Hi everybody, welcome back to Chem 161. More chapter 4 today. And quiz number 3 is due tonight. That is a soft deadline. The quiz will close tomorrow. And then you don't have to think about quantum mechanics for a whole week because it's going to be on exam 2 and the final. So, but I do want to close that down so that I can release the answer key so that you can see it. Because you're going to see it again. You're going to see those questions similar questions to those on exam number 2 and also the final. Where did we leave off yesterday? We left off here. So, I sent you the link to PHET, or FET, I guess we could call it. So we'll put this in here again, just in case you don't have it. Boop, there you go. And so that leads you to the molecular shapes simulation tool, which was, let me capture the window. Boop. This thing. And we were playing with this the other day and putting just shapes together and seeing what it was that whatever we could create. So, all right. So what we're going to do with these models that we're generating out of various numbers of electron groups, or electron domains, or whatever your textbook calls them, we're going to assign these all names. And those names are shown on the slides right here. So if you have 2 electron groups, the arrangement of these is going to be linear. 3 is trigonal, 4 is tetrahedral, 5 is what we would call trigonal bipyramidal, and then 6 is octahedral. So again, let's go through all of these one at a time just real quick. So let me go clear, clear, clear. I'm just going to use single bonds, but you could use any group you want. I could do this all I could do everything in triple bonds if I wanted to, but that would look really silly to some degree. All right, so I'm just going to put single bonds in. So if I have 2, they will, let me turn on bond angles. If I have 2, they will always be linear from each other, no matter where I move them, and we saw that yesterday. When I put the third one in, it makes a triangle. And so you can see that here. And if I move one, the others will also move so that I end up having it all on one plane. So you can see this is flat. It's a flat triangle. And so our text calls it trigonal, but other texts may call it trigonal planar. I call it trigonal planar. So if you hear me call it that, that's where that's coming from. Then we have tetrahedral. Tetrahedral is the first one where we get in 3 dimensions because using all 3 dimensions available to us maximizes the bond angle between our electron pairs, which are these bonds that we have here. If I were to just draw like 4 things coming out of a central atom, up, down, left, right, the angle between those would be 90 degrees. But we can get a little bit further, and so the tetrahedron is the shape that we use for that. Now I'm just dragging it around at this point here. If I put a 5th one in here, then what it's going to do is it's going to go in such a way that I have a linear arrangement in the middle of 3, and then going around that linear arrangement along the equator, if you could think of this as like a globe up and down, that I could just spin around. Oops. It's hard to rotate this one. There we go. There's a triangle in the middle there. So here it is from looking straight down it. Here it is looking at it from the side. And this is called trigonal bipyramidal because if I look at these 3 triangles here, I could say, oh, I can make a pyramid out of this on the top, and I could also have a pyramid out of it on the bottom. So there's 2 pyramids here. And then the last one is octahedral, where it's just a square base pyramid on both sides. Everything's symmetrical. Everything is 90 degrees. You have up, down, left, right, front, and back. So those are our 6 shapes that we're going to be looking at. each of these regions coming off of the central atom is going to be an electron domain. That is either going to be some bonded atom or an electron pair. Notice that the geometry is the same regardless of whether I have an electron pair or an atom there. They all push each other away the same. Man, I could not get my slides to behave there. Because this thing... Oh, no, never mind, that worked. Okay. Now, the geometry for these shapes that we created has a specific term to it. We're going to call this the electron pair geometry. Because it's the geometry or shape of all of the electron groups that are present. Now, another term that you may hear for this, is the Vesper geometry. Those two terms are equivalent. Now, all of the possible Vesper geometries or electron geometries are also shown on this page here. This is straight from your textbook on OpenStax. The reference is on the previous slide. So here's our electron pair geometry terms down here and the angles. You should know the angles because we're going to talk about the angles later. And then these are the shapes in both 3D with our orbitals and also 3D with our structures drawn as a Lewis structure. Now you're going to notice that in 3D we start using these wedges. So what the wedges indicate is that this thick wedge is coming out of the projection, and the thin wedge is going into or behind the projection. So just be mindful that you may start to see those, in our Lewis structures. And that's totally okay if you decide not to use them. What the intent is that they're trying to convey some sense of three-dimensional depth, where everything that is just a regular line, like in PF3, these are all in the plane of the paper. One of them's coming out towards you, and one of them's going behind. It's just an attempt to convey more information. All right. Now, before I go to this slide, let's go back to the PhET simulator here. And we're going to look at water real quick. So let me get rid of all of the stuff. All right, so here's water. This is H2O. My oxygen has 2 lone pairs on it. And you can see the tetrahedral arrangement around the central atom because there are 4 electron groups. 2 are electron pairs and 2 are bonds to atoms. Now, lone pairs of electrons are not bonds to atoms. They're just electrons that are hanging out. But electrons are very small. So, if I were to do this, you could look at my structure and think, oh, that doesn't really look tetrahedral, does it? Like, my electrons are hidden, but their effects are still felt because the effective charge is much more influential in the, or is very influential in the molecule shape. It's what determines it. But relative to the size of the other atoms and the electron cloud itself, those specific electron pairs are very, very small because electrons are very tiny. So we don't see them. And so what we do is we consider the shape without the electron pairs shown. So they're still there. What does it look like without them shown? And so that's what's called the molecular shape. Or I call the molecular geometry because every other source calls it the molecular geometry. And for molecular geometry, you get different terms based on how many electron pairs are present out of the total number of electron domains. So what we're going to do now is we're going to categorize shapes into a second category, which is this, the molecular structure, or molecular shape, or molecular whatever. I call it molecular geometry. And what we're going to do is we're going to omit electron domains in terms of the overall shape, but not their effect. So all the angles remain the same. Excuse me. But what is shown changes. And we're going to get a different shape, which has this chart over here. Shows those shapes. So how do we generate this chart? Well, if there are two electron pairs and the number of if there are two electron domains, and of those two domains, 0 of them are lone pairs, you get a linear arrangement, like we said before. And if you have one lone pair, then you just have two atoms that are bonded together. You don't really have a shape. So this part of the table is just going to be empty because at that point you end up with just two atoms bonded together. But for the next ones going down, our shape changes if we start adding in 0 or 1 or whatever lone pairs. So if I have 3 electron domains, 0 of which are pairs, my shape doesn't change from what our template looks like. I mean, obviously, because we haven't made any modification to it. But if I change one of those domains into an electron pair, then what ends up happening is that the shape is now just this part. And so we get a different term for it. So we can go to the FET viewer here, and we'll look at 3 electron domains. So let me turn electrons back on. We'll get rid of one of them. So here we have trigonal planar. But if I get rid of the lone pairs, now it just looks like a bent line. So I'm going to call it bent. So 3 total groups, 1 is a pair, gives you the bent shape. And so that's how you get the word bent here. Oops, I gotta go back over here. And so let's just go through the entire chart and show you all the possibilities here. So we'll put this back on. And we'll do 4. So here's 4. So if I have 4 electron domains, but 0 are electron pairs, my molecular shape is tetrahedral. In fact, for all of these, the molecular shape and the electron geometry will be identical if there are 0 electron pairs present, because the base shape, which is just what family it's in, how many electron domains are there total, the base shape will be the same as the actual molecule. So now what I'm going to do is I'm going to remove one of these and put an electron pair in. The electron geometry is still tetrahedral because there are 4 electron groups, but one of them is now an electron pair. And so now the resulting shape that I get isn't a tetrahedron anymore. In fact, it looks kind of like a squashed pyramid. So we call it that, Trigonal Pyramidal. It's important to note that this is not flat. You can see that this central atom is raised above my other 3 to make a little pyramid. It is not trigonal planar. If you look at it like this, you could be fooled into thinking that if you just ignored the bond angles or if they weren't turned on. That's pretty convincing, but they totally aren't in the same plane. So just be careful with that. Now what happens if I remove a second one? Now I have the shape for water. This is the shape of water. It's a movie about a fish. I can't spin it. There we go. And when I hide the electron pairs, I get bent again. So 4 electron domains is tetrahedral, but if 2 of them are electron pairs, the molecular shape is bent. All right, we'll go back to trigonal bipyramidal here. This is 5. I'm going to get rid of one of these and put the electron pair in. Now, interestingly, when we put the electron pair in for trigonal bipyramidal, it has to replace one of these, but what it always chooses is an axial position around the center. It never chooses the top, and it never chooses the bottom. So I could just scramble this. So there's my trigonal bipyramidal, and I'm going to put in the electron pair. And it always finds the same spot. And the reason for this is because electron pairs repel, but they repel a little bit more effectively than bonds because the electrons are just hanging out. There's nothing on the other side to stabilize them. That means that the effects of their repulsion are a little bit more pronounced, and they want to be as far away from everything as possible. Well, if I put them at the top in this position, then the only angle difference between them, sorry, this is the top now because I moved it, would be 90 degrees to this plane in the center, right? But if I put it down here, not only am I 90 degrees away from everything else, which is the same, I'm also 120 degrees away from the other bonds this way. That turns out to be better in terms of overall repulsion. So when you have a trigonal bipyramidal geometry and you start replacing electron pairs, they go around the center because there's just a larger bond angle between nearest neighbors. Now, the shape of this is called seesaw, because if I do this and I turn it sideways, and I do it carefully enough, now it looks kind of like a seesaw, I guess. I don't know. I'm trying to make it seesaw. Does it look like a seesaw? Chemists are dumb. We're not great with names, sorry. If I have 5 electron groups and 2 lone pairs, I get this shape. There's my second pair. Again, they go on the center. I'm going to hide all these, and this is called T-shaped because it looks like something. I don't know. Maybe you can tell me why it's T-shaped. I don't know. In fact, I don't think anybody knows. And then finally, if I have 5 total electron domains, but 3 of them are electron pairs, they all hover around the center here. And when I hide them, you get something that looks very linear. So we call it linear. So interestingly, the only way to get linear is to have 2 or 5 electron groups. You could do it with 6, actually, but we're not going to really see that as a common example. But 2 and 5 are very common. And then finally, we're going to... Let me load this back up with single bonds here. So here's my octahedral. This is 6 electron domains, 0 of which are electron pairs, so octahedral, octahedral. A UK chemist named it. That makes sense. That checks out. We're going to get rid of one of these electron pairs, and we're going to add it... Or, sorry, we're going to get rid of one of the bonds and put an electron pair in. So, since these are all equivalent, I could have picked any one I wanted to. I'm going to orient it so it's pointed at the bottom and then hide the electron pairs. And now it looks like we've got a square base of a pyramid. So when there is one electron pair out of 6 possible electron groups, the shape that we get is called square pyramidal. Now, if I remove a second electron pair from this, where do you think it'll go if electron pairs repel everything else more than any other thing does? Well, if you guessed, oh, it probably will go across from the other one. You're totally right. And then when I remove these to omit them, You can see I just have this floating plus. This is how I get the 90-degree angle thing. I have to have 6 electron groups, 2 of which are electron pairs, and this is called square planar. Or your textbook might just call it square. I don't know. Everyone else calls it square planar, so you should call it that too. And really, at that point, that's all you need to know. If I add another one in there, I'll get T-shaped again. And if I add another one in there, I get linear. So you're not going to see those super often for 6 electron domains, though. So just a heads up. All right, that's how we make this chart. If you have any questions about the chart, let me know. Your goal to use the chart is to assign any Lewis structure that you draw or observe. First, you want to assign it in electron geometry. So that's going to be what category it goes in. And all the categories are listed on the left here. Then you're going to want to assign it a molecular structure or shape. And that's going to be which member of the family is that. In fact, if I want to just make it simpler, we'll just do this. So the electron pair geometry will be, so if it's 2, it's linear. 3 is trigonal planar, 4 is tetrahedral. Trigonal bipyramidal, and then octahedral. So you're going to assign one name from this column, and then one name from this table. If I could get the color I want, so you're going to have one from the green list and one from the blue list. So let's do some examples and see if we can figure out some geometry. So what I want you to do, draw the Lewis structure for ammonia. Tell me what the electron pair geometry is and its molecular structure, or molecular shape or geometry. Choose one from each category. So you should have a Vesper geometry, electron pair geometry, and a molecular geometry. I'll give you a minute to draw out the structure, and then assign it a geometry. We'll go over the answer in a second. Once you've drawn the geometry, or you've drawn the Lewis structure and assigned the geometry, type in your answer in the chat. I'm just going to draw the Lewis structure on the slide here real quick. Now, you'll notice that I'm trying to model it to my templates. So now that I have 4 electron domains, I'm going to try and avoid drawing stuff at just 90-degree angles here, because that could confuse me. Or it could confuse you, really. So trigonal pyramidal is a correct answer, but which correct answer? Can you be more specific? Because I want you to give me an electron pair geometry and a molecular shape, or a molecular structure. All right, let's go over the answer. So the first thing you want to do is indicate all of the electron domains around the central atom. So there are 1, 2, 3, 4. So because there are 4 electron domains, the electron pair geometry we would get would be tetrahedral. And then of those domains, how many are electron pairs? 1. So we look at the chart for 4 electron domains, 1 electron pair. And if we go back to that, we see that 4 and 1 is trigonal pyramidal. You don't need the extra AL on the end, so I know that the text says trigonal pyramid and square pyramid and trigonal bipyramid. Every text I've ever looked at and taught from has been pyramidal, so I just call it that still. So that's your answers. The electron pair geometry is tetrahedral, and the molecular shape is trigonal pyramidal. Now, like we said before, whenever you are making these structures, your electron pairs need to be as far apart as possible. So the structure on the left, here, the distance between my electron pairs is only 90 degrees. So this won't form. But here, I have 120 degrees of separation. So that's what the model viewer is trying to do in the PHET simulator. Is it's automatically calculating, oh, I want these to be as far apart as possible. So when I put the second one in, it has to go in a position where I can do that. And not only that, any one electron pair wants to be as far apart from all other bonds as possible, too. Most of the time, that just means that you're going to put extra electron pairs opposite others, or as far apart as possible in regards to bond angle, or just anywhere you want to because all of the angles are equivalent anyway. for example, with 3 or 4 things around the central atom, no matter which one you pick, all the others are 109.5 degrees. It's all symmetrical. All right, so now what I want you to do, I want you to draw these Lewis structures. Most of these you've already drawn, so if you've drawn them from yesterday, just grab your notes and write in another color next to them or something, or copy down your structure. Draw the Lewis structure, then assign it a electron pair geometry, and then assign it a molecular structure. So you should have 2 terms. One will be the family, that's the electron pair geometry, and the other is which member of the family. And remember, if you need to, you can pause the video like right now and just look at this chart. Let me clear all this stuff off of here, or at least clear the ink here. So there's the chart. You can pause and go back to whatever this timestamp is. And then here are the problems for you to do. So I'll shut up now, and I'll give you about 5, 6, 7 minutes or so to solve these. See you in a bit. How are we doing? A few more minutes? 1 minute, 2 minutes, 4 minutes? Let me know. All right, 1 more minute. We'll go over the answers here. All right, so let me go over here. All right. So I'm going to just draw the Lewis structures real quick, since you should know how to draw a Lewis structure by now. So, actually, let me... That's not what I wanted. What scrolls? There we go. All right, so we'll do ozone real quick here. So O, it's not drawing. There we go. Any resonance structure is fine. We just care about the central atom anyway, so how many electron domains are around the central atom? There are 3. So the electron geometry will be trigonal planar. And of those 3 electron domains, 1 is an electron pair. So the molecular shape will be bent. What about these other electron pairs on the outside? We don't care about them, so ignore. They are not around the central atom. We only care about groups around the central atom. So here's SnCl3. How many electron groups are around the central atom? 1, 2, 3, 4. So that means this is tetrahedral. Of those 4, 1 of them is an electron pair. So the molecular shape will be trigonal pyramidal. And then we have SeCl2. That should have 1, 2, 3, 4 electron domains. So the electron geometry is tetrahedral. Of those 4 electron domains, 2 of them are electron pairs. So the molecular shape would then be bent. Here's my carbonate. How many electron domains are around carbonate? Just 3. So the electron geometry for this would be trigonal planar. Of those 3, there are no electron pairs around the central atom. So the molecular shape would still be trigonal planar. Oh, ran out of space, so we'll go over here. For I3-, we get something that looks like this. How many electron domains around the central atom? 1, 2, 3, 4, 5. So that's trigonal bipyramidal. Oops, that's not an I, that's an R. Of those 5, 3 are electron pairs. And so the molecular shape is linear. And then the last one here is IF5, which I believe looks like this. Let me count that really quick. So 42, 8, 16, 24, 32, 40, 42. There we go. And again, electron pairs or sorry, electron domains around the central atom. So there's 6 electron domains here. So the electron geometry will be octahedral. And of those 6, one of them is an electron pair. So the molecular shape will be square pyramidal. All right, there you go. That's geometry. So again, with molecular geometry, your job is to determine both the electron geometry based on the number of groups around a central atom, and then the molecular shape based on the number of electron pairs of those groups that you identified. And this is always around the central atom. Ignore everything else on the outer atoms. Just the bonds to them are what we care about. All right, when we come back from the break, we'll talk about polarity, which is a function of geometry. So we're going to be using our understanding of geometry to figure out how molecules become polar or nonpolar, and then finally we'll wrap that up with a discussion of intermolecular forces. Probably won't finish intermolecular forces today, but that's okay. We'll finish it up on Wednesday. So we'll start the timer. Let me get some more Persona music on here. And we're very nearly at the end here, so let's get some music that's near the end of Persona 4. Welcome back. We'll wind that down here. And we'll get back to it. Oops, that's not back to it. There we go. All right, let's talk about some deviations from these models that we have going on. So, for the most part, these deviations are relatively minor. They just have to do with changes to the bond angle numbers. So, like, all tetrahedrons are 109.5 between any two bonds, the angle between them. But when you start replacing things with electron pairs, what happens is that the angles start to contract away from the electron pairs. So what ends up happening is you see numbers that are smaller than the ideal normal. So in ammonia, the bond angles are 107 degrees as opposed to 109.5. And then in water, they're even smaller still. The overall effect is that any non-bonding electron pairs you have around a central atom take up slightly more space. Their charge influence is wider than that of a bond. And so they push the other bonds closer together. Now, on a test, I'm not going to expect you to memorize these numbers. But what I do want you to know is that, if you see an electron pair, you should say, okay, bond angle is less than 109.5. So you'll need to know that it is not 109.5, but instead it is less than. Okay, and this will always occur whenever you have whenever you have electron pairs that are not symmetrically canceled out by something else. So an example of where they would be canceled out would be if I had something like this, something that's square planar. These are all 90 degrees apart. But when I have these electron pairs here, the electron pairs are going to push these bonds both up towards this other pair and then get repelled by that pair in the same direction. So they don't end up moving at all because these two pairs are directly opposite from one another. Okay. So in a situation where it's directly opposite, the effects get canceled out. But there are very few cases where that happens. The other one I can think of would be linear for when there are 5. So the linear example in the Trigonal Bipyramidal. If you have double or triple bonds, this happens too. Since there are twice as many electrons in a double bond, they push slightly harder. And so what we would say is, okay, these should all be about 120. This one right here should be less than 120 because it's getting pushed by the other two. And then each of these would be greater than 120. Make sure you don't mix up greater than or less than. This is the part in the quarter where I have to remind everybody, the alligator eats the bigger number. Nom 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 nom. There you go. When I did that in person, everybody was like, which one's less than and which one is greater than? I said, remember, the alligator eats the bigger number. And I did the thing with my arms where you mimic an alligator munching. And everybody laughed because that's like something you learn in first grade. So don't forget that. You do need to know that. Now, all of the examples that we have done have had one very obviously central atom. What happens if you have a molecule that's really big? There isn't really a central atom. Well, what we do in that case is we instead just circle an atom and then designate it as the central atom. So I'm going to use the highlighter for this. Now, you'll note that I have omitted the electron pairs on this structure, so I'm going to add them in really quickly. I'm not sure if I did that just as like a challenge or for practice or whatever, but there's all of our structures. So if we look at nitrogen in position 1, we would find that we're just looking at molecular structure. So this would have 4 electron groups and 1 electron pair. So this should be trigonal pyramidal. And if I look at this one, ooh, that's... I don't know why that happened. Here, hold on. Can't see through that one. If I look at this second one here, this carbon number 2, there are 3 electron groups, of which 0 are electron pairs. So this would be trigonal planar. I don't need to highlight them anymore. This carbon number 3, 4 electron groups, none of which are electron pairs. So this would be tetrahedral. And then this last one would be bent because 4 electron domains, but 2 are electron pairs. Now, you'll notice that my structure doesn't represent any of this, and that's just because the structure was drawn in a program that just spit out everything at right angles. So if I wanted to draw the structure correctly and incorporate geometry in it, I'd have to be a little more careful. So there's our answer here. And I'm going to try and draw this so that I have the geometry preserved. So we got our nitrogen here. We'll go like this, and we'll make a wedge. So H, H, H. Here's my electron pair. Now I got a carbon here. I'm going to just spin this around so that it's still trigonal planar here. So there's that. Now I have a tetrahedral, so this will be tetrahedral, and then we'll have this wedge coming out, and this wedge going back. And here's my O. So that's going to go back to the plane, so I'm going to try and draw something like that. There you go. So that's a better representation of what the molecule would look like. And so what you're going to end up seeing in a lot of molecules is that you sort of see this pattern going on. Molecules tend to do this, and that's because the other two things coming out of it require us to have these 109.5 degree angles for each of these spots. I drew under the thing. There we go. All right. I'm not going to have you predict bond angles here because I want to get to polarity today so that we can talk a little bit about IMF. Because IMF and then hybridization are the last two things that we have. That's it. That's the end of the quarter. So I want to get to molecular or intermolecular forces at some point today. All right, so now we're going to talk about polarity. Polarity is a gauge of how much electron density is moved across a bond, right? Well, we can look at an entire molecule and determine if something is polar or nonpolar based on the polarity of the bonds. And so what we're going to do is we're going to use this plan. So the first thing that we're going to do is we're going to draw the Lewis structure of our molecule, but we want to model it after the correct geometry. So no more of this, because this will get you the wrong answer. We want to draw everything with the correct geometry. Use your templates if you have to. Then what we're going to do is we're going to look at all the electronegativities of all the atoms involved. We're going to draw, using arrow notation specifically, because that'll help us. We're going to draw the polarity along each bond. So if I had ammonia, for example, N is more polar than H. Or I'm sorry, N is more electronegative than H. So I would draw an arrow like that. And we're going to do that for each bond. And then finally, we're going to add all of those arrows together. We're going to do vector notation addition. And we're going to determine where the electrons got moved to. Because polarity is just electrons being shuffled across a bond more in one direction than the other. They're going to move in the direction of the arrow. So we're just going to follow the arrows. If we follow all the arrows and we end up away from where the electrons started, then that's where the electrons end. They ended somewhere different than where they started. The molecule must be polar. I don't know if you can hear that plane outside. It's flying right overhead. I live next to Boeing, and this is the first time I've actually had this happen during my class. So now, if your electrons get shuffled around, but they end up... Oops, can't see that. If your electrons get shuffled around, but then they end up back where they started, your molecule is nonpolar. So this happens if you have arrows that are pointing directly away from each other. And we're going to see examples of that in these few slides here. So on the board is CO2. And we know that the electronegativity... You can hear it outside too, yeah. We know that the electronegativity of oxygen is 3.5 and carbon is 2.5. So that means that oxygen is the negative side of this polar bond. So we're going to draw our arrows pointed towards each oxygen. We also know that there are 2 electron domains around the carbon in carbon dioxide, which means that the geometry of this would be linear. So these are pointed directly apart from each other in a 180-degree angle between them. So now what I'm going to do is I'm going to add the arrows. The way that you add the arrows together, or vectors, if we're going to do this in physics, is you add them head to tail. So if this is my first arrow, and this is my second arrow, I would put this starting point right here, and this would be how I add them. And the result would be, I then connect where I started to where I ended. So that would be this. So the result would be this arrow right here. And I can do that for as many vectors as I want to. So we're going to do that for these 2 vectors, and I've already programmed it in here to show this. So here's the first arrow, and that's where I started. I'm going to put the tail of the second arrow on the tip of the first arrow to add them together. And I ended in the same spot. So what does that tell us? Well, one bond pulls our electrons in one direction. The other bond pulls the electrons in the opposite direction. The end result is the electrons are more or less in the middle where they started. So this molecule has no polarity. We would call it nonpolar. Now, with linear molecules, that's really easy to see. But what about something that's triangular, like this? How does this work? Now, I've removed the plus end. I'm just drawing arrows because it's a lot easier for me to draw arrows in PowerPoint than it is to put the little crossbar and then animate both. So we're going to do this for SO3. So here we go. There's the first arrow. And what do you notice about where everything ended up? Despite everything being pulled in all directions, the end result is they all cancel. So SO3 is nonpolar. But with water, you can clearly see that I'm going to end up higher up on the screen than where I started, no matter which of these I do first. And yes, you can add these in any order, because just like addition, you can add any numbers in any order you want to. You get the same result. So with water, I ended up in a different spot than when I started. So we would say that water is polar. And more specifically, if the arrow points at the negative side and the start of the arrow is the positive side, I can then put that on the structure itself. So the oxygen side of water is the negative dipole end, and the hydrogen side is the positive dipole end. Now, these are partial charges because these are covalent compounds. We're not moving an entire electron. They're not ionic. So we would use the delta symbols. This feature is going to be really crucial for talking about intermolecular forces in the next section, which is Unit 10. All right. Now, I have some tetrahedral examples in here. Tetrahedrons are really hard to draw on paper. And it probably took me like 40 minutes to program this first one. But you can see that if I sum these together, even though it looks really funky, it still works out pretty good, right? As long as you have the geometry correct. But if you're missing any of those arrows, then the end result is that you get displaced from the start. So, again, we would do the same thing. This is the delta minus n, this is the delta plus n, so we would draw that over here. Now, on paper, what I would try and make you do is that I would ask you to not only indicate is it polar or nonpolar, yes or no. I would also make you indicate direction of polarity, as in which side of the molecule is delta minus. So it's important to know both of those things. As far as solubility is concerned, we really only care if it's polar or nonpolar. So in the next section, when we talk about will these two things mix together, polar and nonpolar is what's going to dictate it. But knowing which end is the negative side will help us explain it in a little more detail. All right. Your structures are not going to be as good as these because, one, I made the computer draw the structure for me, so it got the angles perfect. And then, two, even though my arrows aren't perfect, I just sat there and tinkered with it until it was. So I took hours to make these slides, and this was actually for a job interview, and they loved this. They very nearly hired me, but it was for a class that I told them I didn't really like teaching. And that was what they were hiring for, unfortunately. So I could have had a full-time position at Seattle Central if I told them, "Hey, I like 121. It's great." It's not great. I'd much rather teach 161. There's nothing really wrong with 121, I should say. I prefer 161. Okay, so just to summarize, this is what we have done. Draw your Lewis structure as best you can, adhering to all of the geometric properties of the shapes that we studied in the previous section. And then draw the polarity arrows, and then follow the arrows. They show you where the electrons go. If the electrons end up with no displacement, they ended back at the start after you've done all your arrows. There's no net movement, and the molecule is nonpolar. But if the electrons do get pulled away, there is a net dipole, and the molecule is polar. Now, one thing we haven't discussed, all of these examples that we were doing had all of the bonds have the same atom. And so all of these arrows, even though they were drawn kind of funky, they have the same magnitude. Because the magnitude of each of these bonds is just the difference in electronegativity. And so if I had delta En was, say, 0.6, I might draw an arrow for that. But if delta En was 1.6, I would draw a much bigger arrow. I have sort of abstracted that with the assumption that, oh, all of the bonds are the same, so I'm going to draw all the same arrows. And then they're in 3D on a 2D paper, so it looks a little funky. But what that means is that if later on, if I give you other molecules, for example, this molecule right here, where I have different atoms bonded to it, you actually will have different length arrows that you should consider. And the one that's more polar should get a bigger arrow. But in this example, you can actually still solve it because the arrows don't point all in the same direction, as you'll see. So what I want you to do is draw the Lewis structure, look up the electronegativity of all the atoms, and then point the arrows at the more electronegative atom along each bond, and then determine is the molecule polar or nonpolar, and in which direction through the molecule. I'm going to go draw the Lewis structures while you guys are doing that, so we will have all of that set up. And then we're just going to plop polarity arrows all over it, and we'll see what we get. Okay? See you in a bit. I'll give you like 5 or 6 minutes to do this. All right, 1 or 2 more minutes. We'll go over the answers. All right, so I've drawn all these out here, so I'm just going to take this and just shove it in the corner here. All right, so I'm going to do new layer. So I could just draw all over this all that I want and erase it all I want. So when comparing electronegativity, the fast way to do a comparison, you could look up the numbers if you want to, but since we don't really care about the numbers so much, we just compare about which one is higher so that we can point the arrow at it. Just find the element that is further to the right or up. And so that's chlorine between phosphorus and chlorine. So my arrows are going to point away from chlorine, or away from phosphorus towards chlorine. Now, if I add all these together, and that's really easy to do on a computer here, so I can just take this and oops. Yeah, I could take this and oops. So there we go. So we'll take this one, and then we'll take this one. And then we'll take this one. All right. Did I end up where I started? No, I ended up basically displaced like this, right? So this molecule would be polar. Now, obviously, that's impossible to do as effectively on paper, but you can approximate this by just like using your fingers and then moving your hand and drawing an arrow between your fingers. Do the best that you can. All you're trying to do is approximate it, and if you could see, oh, it clearly doesn't end up where it started, you're in good shape. This one, much easier, because they point opposite from each other. And when I go to select them and move them, I'm just going to stack this one right on top. You could see, like, duh, they end up right on top of each other, so this one's nonpolar. Over here, let's do the same thing. Chlorine is more electronegative than carbon. And I'll just take my bonds and I'll move them around. But what I'm going to do is I'm actually going to take this bond and stack it on top of this bond to show that those neutralize each other. So the end result is, if I just added those two things together, the result would be 0, right? And then if I do that over here with this one I get 0 also, right? Well, 0 plus 0 would be 0, so the overall effect is... Oops, I gotta hit all here. There we go. It's not working. Why is it not working? There we go. Nonpolar. So, again, arrows are vectors, and we can add them in any order we want to. And if I add two vectors together and get 0, That's the same as if I'm not adding a vector at all. So you can take vectors and just try and cancel them out. We're going to do that again down here where we have this one and this one, and we might as well just cancel these two because they point apart, right? We'll get to that in a second, though. Let's look at C and H. C and H are essentially nonpolar because the difference in electronegativity is so tiny. We're including it for more of a proof of concept here. But without even doing the addition, you can see that everything's kind of doing this, right? It's all pointing towards the Cl, and there's nothing to cancel it out. So without going into too much detail and dragging all the stuff around, you could tell that this is polar, and the overall direction would be like this. All right. For SCl4 over here, I've got one that goes this way and one that goes that way. Those aren't going to cancel out because there's nothing pointing back to the left to fix it. So when I drag this guy over here, you could see that the overall result... that's not what I wanted to do. The overall result is just this. So this is polar. And then for IF5 here, these two are going to cancel each other out. These two are going to cancel each other out. And it doesn't matter what orientation you did them. As long as you did the correct geometry, which is square pyramidal, you're going to have a square, and the ones in the square will cancel, leaving only this one, which is the overall. All right, so there are your answers. And again, your job will be to determine polar or nonpolar, and then indicate the direction of polarity. Whenever I say direction, I mean the negative side. I do the wrong molecule? Yeah, I did. Oh. Well, you got a bonus molecule. You got C2Cl4 instead. But when we go back over here, I'll just quickly draw C2Cl2. C2Cl2 is linear, and so it's going to be very obvious that the dipoles cancel. So there you go. And so the arrows for this would point this way, and they would just cancel each other out. So this one is nonpolar also. Yep, you're exactly right. They're nonpolar. All right, I have about 10-15 minutes left, so I'm going to get started on intermolecular forces. We'll finish this up tomorrow. It looks like there's like 50 slides in here, but the last like 15 or 20 are actually a demo, which if I have time, I'll talk about it because it's really cool. Let's talk about intermolecular forces. All along, we've been talking about bonds. That's been the whole theme of Chapter 4 is bonding. Now what we're going to talk about are the attractions between molecules themselves. So the attractions within molecules are bonds. Atoms are held together through bonds. But molecules are also held to other molecules through what are called intermolecular forces. These are not bonds. They are weaker than bonds, but they are significant enough that they can give molecules specific properties. For instance, if we look at molecules in the gas, liquid, and solid phase independently, what we could say is that, well, in gas molecules, the particles are very, very far apart, and so the interactions between them would be very weak. Whereas in a liquid, the molecules are much closer together, and so those molecules are held together by something. Otherwise, they would just expand apart from each other, because all molecules move, right? They move in straight lines until they bonk into something, or some other force causes them to change trajectory. With a solid, you could also say that the interactions are so powerful that the molecules don't move at all. For example, in ice, if you look at an ice crystal, the water molecules are aligned in such a way that you get a solid. If the molecules were moving, the ice cube would flow, and it obviously doesn't do that because it's a solid. So we know that in a solid such as ice, those water molecules are not bonded together because they're all independent water molecules, but there must be something that holds them into place. And that something is called the intermolecular force. Intermolecular forces are responsible for the phase of matter that you see for molecular stuff. Why is water a liquid at a specific temperature versus a solid at a different temperature? And why is it a gas at a higher temperature? We're going to examine these intermolecular forces to show how molecules can hold each other in place depending on what the molecule is. And the major feature that we're going to look at is polarity. So the reason that we just did that discussion of polarity was to look at this, which is to say, okay, if molecules are polar, they stick to each other because now they have charged components. They're like magnets. They're mini magnets. Other molecules might not have that. They're nonpolar, so they don't stick to each other. So let's look at that. So again, that's going to be our guideline. Strong forces hold molecules together. Weak forces allow some freedom of movement. And then weakest or almost zero forces cause no interactions at all. So in a gas, the molecules hardly even see each other. They're just too far apart. We're not going to do this demo because you're not in a classroom. I forgot about that. So that was my intermolecular forces demo. I'll talk about the demo. So what I do is I have everybody stand up and leave the classroom. Don't do this. Don't get up and leave your apartment. It's dangerous out there, and also it's cold. But in part 2, I would have everybody join hands so that they're one contiguous chain. And then I would say, try and leave through the classroom like you did before. And obviously what the problem is there is that you want to leave the classroom, but you have to wait for the person in front of you, and you're also dependent on all the people behind you. So if one of them is trying to get up from their chair, or they got stuck on something or whatever, you have to wait. And so in part 1, where you're independent, you're a gas, and so you have freedom of movement. You can go in any direction you want to. But in part 2, a force holds you together, and that is the force of you joining hands. And that force would be the intermolecular force. And then I joke about how part 3 is now use the supplied manacles to handcuff yourself to the table and then leave the room. And nobody can because that now you're a solid. So how do we move between phases? This is the common one that we look at, heat or cool. When you heat molecules, they move around more quickly. So if my molecule is moving around slowly at a given temperature, if I heat it up, it will then move much more quickly. All molecules have kinetic energy, even those that are stationary. If you're a stationary molecule, such as that in a solid, what ends up happening is you don't move, you wiggle. You vibrate back and forth. As you increase that vibration, eventually you get enough kinetic energy where you go boink, and then now you can move. I mean, that's kind of an analogy, yeah. Now, things that are moving faster are harder to hold together. You can kind of see this in action if you have a magnet and you hold it against the fridge and you have it really close and you let it connect to the fridge. It will just go snap right on there because it's moving very slowly. But if you take the magnet and you hold it some distance away and you try and drop it, it will eventually get attracted to the fridge, but it will fall significantly farther before it does that, and then it will slide afterward. It might even slide off the fridge. So if you have motion or kinetic energy, your molecules still want to stick to each other, but they're unable to do so because that kinetic energy is working against them. And then in a gas, there's just so much kinetic energy that you can't possibly get your molecules to be close to each other for any given time because they're just going so fast and they're so far apart. So this is why temperature changes phases. When you heat something up, you add kinetic energy and you move from a solid to a liquid to a gas. When you add enough kinetic energy, you overcome the intermolecular forces. If you remove kinetic energy by cooling something, you'll eventually go from a gas down to a liquid to a solid. Now, the other thing you can do is instead of increasing or decreasing temperature, you can modify pressure. So if I force all of these molecules to be close to each other by pressurizing the system, then eventually they get constrained to a small space and they become a liquid by virtue of them being attracted to each other, even though they still have very high kinetic energy. If there's nowhere for them to move, they become a liquid. And you can pressurize even further to make a solid, but that's really hard to do. And it requires extreme changes in pressure. So temperature is by far the easier way to do this, but pressure can also accomplish the same thing. The key feature is that to move from phase to phase, you have to either amplify or diminish intermolecular forces. You amplify them by removing kinetic energy so molecules are slower, or you diminish them by heating up the molecules so they move faster. And then this is just my picture to show you can push molecules together and they will eventually compress into a liquid. This is how you compress things like butane. Butane's a gas at room temperature, but if you put enough of it in a container and seal the container, it gets compressed and it becomes a liquid. Now, all intermolecular forces follow the fundamental law of electrostatics. So Coulomb's law again. And again, we don't give a shit about this part of the equation. We only care about this part. Now, bonding also follows these properties, and so do just atoms, like the electrons floating around the nucleus, are going to be attracted to each other. But what's important in this equation is that instead of using whole numbers like we would be using for electrons around a nucleus or ionic bonding, instead what we're using now are partial numbers. So these are decimals, which means that because these are smaller numbers than 1, this force goes down. The second thing that we're going to consider is that on the distance of bonds, bonds are way longer than an electron's distance to a nucleus. So this number is going to be considerably larger because my molecules have to get close enough to each other, and that's not going to be less than the distance between an electron and its protons. So the distance between particles with these forces will still be great, and this will make this lower still. So the energy that goes between intermolecular forces is going to be considerably weaker than that of a bond. And so this is why, if I have water right here, and I have another water molecule, we'll just put a second one here, and I have some sort of interaction here, which I'll just indicate with a highlighter. So some interaction might hold these molecules together. If I apply heat, the first thing to break is this, because it's the weakest interaction. If I apply enough heat and enough energy, then I break these bonds too. But they do not break first. They need considerably more energy. So whenever you add energy, you will vaporize something from a liquid into a gas before you start breaking all of the bonds in it. In almost all cases, the smaller the molecule, the more likely this is to be true. Now, for some giant molecules, they will decompose before their intermolecular forces split because the intermolecular forces can get significant if molecules get bigger. And we'll talk about those intermolecular forces in more detail really tomorrow, I guess, because we're out of time. So So just in case you're going to be reading ahead, there are 4 intermolecular forces that we're going to cover. We're going to talk about dispersion. We're going to talk about dipole-dipole. We're going to talk about hydrogen bonding, and then ion dipole. So those are the 4 forces that we're going to talk about. I have ordered them in the order of weakest to strongest. But now that you've seen the background and you sort of have an idea of what an intermolecular force is, when we come back tomorrow to discuss the rest of this, we can go through the remainder of the chapter in probably the first hour or so, talk about all 4 forces. We'll be able to rank them. And then that'll be it for chapter 4. And then chapter 5 is literally... I could write it in the first minute of chapter 5. I'm going to write down a table and say, here's chapter 5. Learn this table. And then we'll talk about what chapter 5 actually is. And it will be... It's much simpler than it will appear to be. It's like chapter 5 is... I don't know why. It's 2 minutes long, but... I don't know. Alright, well that's all I got for today. So... Let's see, what do we got on the agenda coming up that is worth mentioning? So there is a quiz for Unit 4. We're going to finish the chapter tomorrow, so that'll be posted. But the deadline for that quiz is actually going to be relatively short. I'm going to make the deadline Friday, because that'll put last call on Saturday. You'll be able to see all of the answers on Sunday, and then you can have those available to study for the exam, which is on Monday. Okay? I know we talked about it on the syllabus at some point. I think the syllabus says the exam's on Friday. I'm going to move that to Monday for next week. And then the final will be later on that week. And somewhere between that will be a review session, which I'll send out an announcement for. And we'll just poll the class. What day do you want the review session on? Tuesday or Wednesday or whatever. And yeah, that's it. So we are very, very near the end. Believe it or not, after all this time, we finally got there. So don't give up yet. The end is in sight. We'll see you tomorrow for the last lecture.